Good afternoon. I'm Ananta Chandrakasan, Dean of Engineering at MIT. I'm thrilled to join you for the launch of MIT.nano, a world-class facility for research focused on nanotechnology. I would like to congratulate Vladimir Bulovich, the founding director of MIT.nano, and his wonderful team for their amazing work in launching this facility while deeply engaging the broad MIT community. MIT.nano will enable the science and engineering of new materials, devices, and systems based on innovations at the nanoscale dimension. The facility will spark invention across campus and beyond. Over 2,000 MIT faculty and researchers from across MIT are expected to use the new facility every year. It will enable basic discovery, facilitate innovative design, and inspire new systems. The research will drive and impact a spectrum of areas, including sensors, quantum computing, next-generation communications, artificial intelligence, health, energy, transportation, and much more. The facility will help advance the physics of AI and connect to institute-wide initiatives like the MIT Quest for Intelligence. We expect to see new innovative approaches, including neuromorphic computing, new memory devices, and systems with 3D integration. We look forward to active collaboration with industry. The facility will also support innovation and entrepreneurship, allowing efficient prototyping. I look forward to the discoveries, the inventions, and the hard tech startups to come. Among other things, MIT.nano will support a diverse array of efforts and expand the opportunities for interaction between MIT's main campus and the most advanced developments of MIT Lincoln Laboratory. It is my pleasure to introduce Eric Evans, director of MIT Lincoln Laboratory, a multidisciplinary, federally funded research and development center run by MIT for the Department of Defense. Eric is responsible for the strategic direction and overall technical and administrative operations of a laboratory that has 4,000 employees whose backgrounds include electrical engineering, physics, mathematics, and computer science. The laboratory focuses on advanced technology development and system prototyping for national security needs. Eric is currently the vice chair of the Defense Science Board. Eric is a fellow of the IEEE, a fellow of the AIAA, and a member of the National Academy of Engineering. In 1996, he and his co-authors received the M. Barry Carlton Award from the IEEE Aerospace and Electronics Systems Society for a paper on advancing radar signal processing. He will join us now to describe some of the most exciting developments in Lincoln Laboratory enabled by the nanoscale. Please join me in welcoming Eric.
Ananta, thank you, and Vladimir, thank you for inviting me to speak this afternoon. And it's great to be here for this wonderful event on campus. And Vladimir asked me to talk to you a little bit about the impact of nanotechnology on the work we do at Lincoln Laboratory. And I thought I would start by describing in a little more detail what we do. And we are a facility in Lexington, Massachusetts, about a 45-minute drive away. And this is how we look from the outside. We do a lot of work for the Department of Defense, but we also work for the Department of Homeland Security, the FAA, NASA, and other organizations. And we have three main roles. We do what's called architecture engineering. So we look at how big systems come together, what sensors, what networks, and other technologies that should come together around a new idea. We also take the long-term view on technology. So we might look out 10 to 20 years in a technology area to incubate it, to make it available for prototyping later on in big systems. And what really makes us unique is we do prototyping on a grand scale at Lincoln. And at any given time, we might have between 15 and 20 very large prototypes at the scale of $20 to $250 million over a few years to create something dramatically new. So our role is to take on high-risk, high-payoff projects and to create the first copy of something, and then when we're done, we transition it out to industry or to startup companies, or in some cases, into operations. We also have a microelectronics facility shown here. Will Oliver talked about some of the partnerships we've developed through this, and this has about 70,000 square feet of space, about 18,000 square feet of foundry space. And this is a real driver for Lincoln. And a lot of advanced electronics flow through this facility to help us to drive the advanced prototyping that we do. And I'll show you some examples of how that works. So we have a whole range of projects. On this side of the chart, we have our projects at the component and the subcomponent level. And these are various technologies like advanced focal planes, avalanche photodiode arrays, quantum bits. I really enjoyed the quantum session this morning. New miniaturized transceivers for various applications. And on this side of the chart, we have the big prototypes. And these are projects that cover new telescopes, new ways of doing surveillance to protect soldiers in harm's way, new radar systems for advancing what the FAA needs for tracking aircraft and weather, and new satellite capabilities. And I'll touch on a couple of these throughout the presentation. The challenge for Lincoln is to maintain the balance across this chart. So we try to feed all of these technologies into the advanced prototypes we're doing, but we also try to inform what we ought to be doing on the technology side based on the system needs. So there's a nice dynamic back and forth for us to plan what we do next. One example of a project that is a very, very strong partnership between MIT campus and Lincoln Laboratory is this Transiting Exoplanet Survey Satellite program. So it was a project led by the MIT Kavli Institute with support from MIT Lincoln Laboratory, NASA Goddard, and many others in the community. And the idea was to create a probe with very sensitive cameras that could scan a whole range of stars to look for Earth-like and super-Earth-like planets out there. And to make this work, the cameras had to be very, very sensitive. So Lincoln Laboratory was involved in creating the focal planes for this system. We, in our microelectronics facility, developed focal planes with very low noise and a very wide dynamic range and integrated that behind a very sensitive camera system. And there are 4 of these systems right here shown in that satellite. And it was launched back in April. It's in the position now to begin collecting data. This was first light collected earlier in the summer. And there are 200,000 stars in this image. And so what this is doing now is looking at this very carefully and looking for planets transiting stars, looking at changes in intensity, and identifying planets for future exploration and measurements later on. So a lot going on, but this is a program that was very much driven by nanotechnology and advanced electronics. Another example. You've probably all read in the press, we're very concerned about the protection of our space assets, and we were asked by the Air Force to create a new telescope system based on new technology to be able to scan the hemisphere and look for objects that might be of concern to us. You imagine threats to GPS or our comm satellites or other satellites that are up there. And to do that, we had to create a new telescope system. This is what it looks like over here. It's a Mersenne-Schmidt design. It has 3 large mirrors, some of them aspherics. We've worked with L3 Brashear to pull together some of the main components for this. And it has a very short focal length to give it the field of regard to look for the objects that we're concerned about out there. And the problem with that is with a very short focal length, the imaging surface isn't exactly flat. It's actually slightly curved. And that would create problems for the imaging. So what we did to address that is we created focal planes in our microelectronics facility that were so thin that we could conform them to that imaging surface. And we created the first large curved focal surface ever developed for a big telescope like this. And that's shown right here. We developed some other advanced components. I can't show you the national security data behind this, but I can show you some of the science data. This is an image of the Eagle Nebula. You can imagine with a large field of regard, you could do synoptic astronomy and look at a whole range of stars that might be changing over time. So the system has already identified over 6,000 variable stars, and about 93% of those were not in the original catalog for that. So a lot of great science work is already going on with the system, as well as the national security work that's a part of it. Another area of advanced technology that has driven the sensing work that we're doing is related to avalanche photodiode arrays. And what this is at a simple level is it's a p-n junction set up in a way that a single photon will create an avalanche of electrons that can be detected by a timing circuit up here and then reset very rapidly. And we can create arrays of these avalanche photodiodes to create a capability for measuring angle information that might be collected by a laser system or an optical radar. So we've been developing technology like this for many, many years and implementing it into various large systems, some of them for national security, some of them for other applications. And I wanted to show you a couple of examples. One is a LiDAR system for doing ground surveillance. So what we did is we created a LiDAR system over here in the IR band, and it has reasonable power, a good low-loss optical system. We put all that together and then integrated it into a Sabreliner aircraft for collecting data, looking down. And the first test campaign was in Puerto Rico. And when we took it there, we discovered something very surprising. Because of the avalanche photodiode arrays being able to detect individual photons, we found that we could look through foliage down to the ground to see things you wouldn't normally see from an aircraft. So we developed that capability, and this image over here is showing an example of some data collected in Puerto Rico. You can see trees, you can see some trails here. The dark red is high, and the other colors, blue and green, are low. And so I wanted to show you what we can now do with this. Since we have 3D information on what's on the ground, we can then go back and synthetically walk through the data and find things that you wouldn't normally see from an aircraft in search of something. So that's next. So you can see the trees. We can then go underneath. There's a trail. Here's another trail. We can walk down. And then as we're going down the trail, you can see some interesting features. So here's a wire that indicates something might be there. There's a tent. And you can see some other tents here. And then just pulling back a little bit, since we have the range information, we can time gate out the trees and then discover the whole encampment right in here. So you can just imagine the many applications for that, not just for national security, but for archaeology. And this has already transitioned into use for national security needs. But we could imagine another application. And so what we did on the next chart is we recognized that this LiDAR capability could be used for humanitarian assistance and disaster relief. So what we did is we got money from FEMA to create a new LiDAR system here with more power and the ability to scan over wider areas, and we integrated that in an aircraft shown over here. And the idea was you could deploy this after a national disaster like a hurricane, look for people that might be stranded, find roads where supplies could move, or areas where aircraft or helicopters could land to provide supplies. But also we learned that they were having difficulty with the cleanup because so much of the debris characterization after a disaster is very manual, meaning people have to walk out into neighborhoods, find debris piles, characterize how big they are, and then they roll everything up, and it takes literally many weeks to months to get things cleaned up. So after we had participated in the early disaster relief effort, we had an idea where we could fly over after Hurricane Harvey in the Houston area over about 700 square miles with about 12 passes and collect all the data needed to characterize the debris that might be out there. So in one day, we could characterize how much debris might be out there, which would save them literally tens of millions of dollars in the characterization effort. So in the next video here, this is a neighborhood in the Houston area. you can see roads and you can make out some houses and trees and everything. So what we applied to this were algorithms to automatically remove some of the objects that we could identify. So we could remove trees, we could remove houses, we could remove cars on the road, and then eventually reduce it to what we could identify as the debris piles, which are shown here. And since we have the 3D information, we can compute the volume, we've got the location, we can roll all that up automatically, and then they can roll out the trucks to take care of things in a much more rapid way. So this is also already transitioned to FEMA, but very much driven by advanced nanotechnology to make all this work together. And we have a whole range of other ideas like this to help with human needs around the world. We've also used avalanche photodiode arrays for laser communication. And this was a fascinating project with NASA where we were given the opportunity on a probe that was sent to orbit around the moon. It's called the Lunar Atmosphere and Dust Environment Explorer up here. This is a probe. It has a laser system on the side that we put on. It also has a ground terminal that we prototyped. One of the innovations in this system is a superconducting nanowire array that we developed with joint research on campus that can detect individual photons and reset very rapidly, which made the receivers down here very, very sensitive. And because this was so good, we could have a small aperture up here, and what I find amazing is we could communicate from the moon down to the Earth with over 600 megabits per second on half a watt of laser power. So you can just imagine the applications of that. So all of this has transitioned through NASA, so future probes out to Mars, Jupiter, and beyond will have links like this to download the data very rapidly, which is growing in volume with the advanced systems that they're deploying. Another area for advanced technology and nanotechnology applications is with radar development. And you may know that the US has a whole array of radar systems to help with FAA tracking of aircraft, but also for doing homeland protection and weather sensing. And there are about 550 of these radars nationwide. Many of them were built back in the 1960s, and then many of them don't perform very well. So we were asked by the FAA and others to prototype a new system over here, which is an advanced phased array radar. Each one of these little squares in here, little tiny squares, and there are about 5,000 of them, is an antenna element. And this radar system can scan electronically to look for aircraft and weather that might be of concern. And we can scale the radar up and down as needed. In some cases, we might want a larger version for homeland protection. And the idea is to replace all of these radars over here with about 350 radars of this design. And each one of these radars is about 1/10 the cost of one of these over here, because we can mass produce these antenna TR modules and elements and piece them together into a radar system. So this will change fundamentally how we do surveillance nationwide and help the nation to protect itself better from another 9/11-like attack or other concerns we have for homeland protection. And this is now in Norman, Oklahoma, being demonstrated, and if successful, this will transition to contractors to produce all this at scale. It'll probably be about a $7 or $8 billion acquisition program. So the technology here was very much driven by microelectronics, but there's another dimension to it driven by microelectronics. The high cost aspect of radars turns out to be the high power amplifier, which transmits the energy. And we're developing new ways of using wide bandgap materials, gallium nitride, which puts more of the power in the voltage rather than current, to allow creating high power at much lower cost. And the idea is to use various techniques. The best is to put gallium nitride on silicon wafers. We can run 8-inch wafers through our microelectronics facility relatively cheaply, and that reduces the cost per watt for these high power amplifiers by more than a factor of 10. So this will reduce the cost of these radars even further than I mentioned before. And we've already created the first prototype of gallium nitride on silicon for a 10-watt module for a frequency called X-band, which will be propagating out. So this technology is already getting out there. So where are we going? This is the last chart. We, this year, got money from the Department of Defense to create a new facility right at the edge of Lincoln Laboratory for our non-silicon work. This will be about a 160,000 square foot facility with about 36,000 square feet of foundry space for us to develop new technology. This is what it will look like. and we'll be breaking ground about a year from now, and there will be many opportunities for collaboration with research on the campus through this, as well as the national security work that we're doing. So it's a very exciting future for us, and we are very much looking forward to a great partnership with MIT.nano as we advance all of this. So thank you.
Well, it's my great pleasure to tell you about the next set of talks that will focus on materials development and nanotechnology. Besides all the labs you have heard of up to this point, there is another laboratory right next to MIT.nano, Building 13, next to Building 12, that MIT.nano will carry. Building 13 is so known as the Materials Research Laboratory, focused on the ways of advancing ways of using new materials for a variety of purposes. MRL has been in existence for 1 year, as of actually today or just a couple of days. It's about 1 year anniversary of its existence, yet it has a storied history that stretches over the decades in the previous instantiations that were known as the Center for Materials Science and Engineering and the MPC, Materials Processing Center. Result of it is that there is a tremendously close collaboration between the present MRL and the emerging MIT.nano. And I have asked the director of MRL, Professor Carl Thompson, to indeed take over and tell us more about our materials session. Please.
So I'm very excited to be here at this incredible event, a transformative event for MIT. And also very happy to have the opportunity to chair the session on materials. Vladimir asked me to say a few words about the Materials Research Laboratory, but he didn't leave a whole lot of words to say. But it is a brand new laboratory, but it was formed by the merger of two centers that had existed both for more than 30 years. And the formation of the MRL and the advent of MIT.nano is not a coincidence. The formation of the MRL was done specifically to create a better partner for MIT.nano. So our principal goal is to support interdisciplinary research at MIT. Interdisciplinary research carried out by people from across the institute. So we're a partner for MIT.nano, and as Vladimir pointed out, we are right next door. This is dated. That's not a real picture of MIT.nano, but now there's a real MIT.nano there. The MRL is right next door, and we're connected at 4 floors. And that's a wonderful opportunity for the materials research community to interact with MIT.nano this closely. I want to make a quick plug for an event coming up next week on Thursday. There is going to be a full-day symposium on materials research at the nanoscale, focusing especially on imaging techniques, and I'll say a bit about that later. Okay, materials. What are materials? Well, this is kind of obvious. Materials are crystals, they're glasses, they're gels, they're even liquids. That's one way to think about them. You can think about them in terms of their properties: semiconductors, ceramics, metals, polymers. Those are the most common divisions of the types of materials there are. And then, of course, there's new materials that are fabricated, composed of these other materials. And just a few examples are biomaterials and metamaterials and nanomaterials. So when you say materials research, it's about all of these things. And so what is materials research? Well, I think a useful way to think about it is in terms of the interplay between these various activities. The first one being, how do you make a material? You can make a material an atom at a time using the sorts of techniques that we're going to have in MIT.nano, or you can make them tons at a time. So what's the commonality there is how you make them determines what their structure is. It determines their structure at a nanoscale, an atomic scale, and at a mesoscale, and ultimately at a macro scale. So that's an important part of materials research, is understanding those relationships. Another important part is understanding how structure, and of course composition, affect properties: magnetic, photonic, electrical, mechanical, and on and on. And then finally, as you explore these relationships, you do that in order to make new materials that have new functionalities in existing systems, some of which are shown here, and create new functionalities such as nanoscale devices. Now, I want to make a couple of important points here. All of these activities are going to be greatly enhanced by the existence of MIT.nano. In particular, one of the things that has already happened is the advent of MIT.nano has made it possible to very much up MIT's game in imaging in a variety of ways, but especially electron microscopy. And you heard a little bit about cryo-EMs this morning. There's a couple of new faculty members, one of whom you'll hear from this morning, that were attracted to MIT by the possibility of the work that they can do in MIT.nano that could not be done in any of the other buildings on campus. You use these tools to study structure. You can study structure at the atomic scale, and you can also now study structure at the chemical atomic structure, the chemistry of atoms. And that's an incredible and new capability, and it's a capability we'll have here at MIT, and that we'll be able to advance. And we have a new faculty member who's using AI, for example, to improve our capabilities for that. The other thing this microscopy does, though, is more than just characterization and looking at structure. You can also watch how materials are made at the atomic scale. And Frances Ross, who you'll hear from, is a leader in that area, and she's brand new to MIT, largely because of MIT.nano. So, another thing here is nanoscale structure is important in the performance of large systems, like automobiles or like buildings. And in fact, structure at all length scales, but especially the nanoscale and the properties at the nanoscale, control the properties and the ability to make large structures. And you'll hear from Marcus Buehler, who will talk to you about not only that relationship, but some very new ideas about how to design over those length scales. Okay. And it all starts at the nanoscale. Okay, so not only can this process, and this process is practiced by people in all the departments in the School of Engineering, most in the School of Science. You've heard from many of these folks today. I should back up here if I can. Okay. So there's a lot going on here, and you heard almost everybody today talked about a material and using material, at least in a new way. And so many people at MIT work on materials research. At least 150 faculty, and of course then a couple of thousand, several thousand students and staff and postdocs. But they have this in common. Now, in many cases, people focus on the relationship between how you make something and its structure. Many times, people focus on the structure-property relationships. Some people do the whole circuit, and that, of course, feeds back into making materials in different ways. But very often, these segments have experts in different disciplines. And so doing this circuit requires interdisciplinary research. And that can lead not only to new materials for existing applications, but also new materials for new applications. And sometimes that leads to entrepreneurship. And I wanted to give an example of that. This is work that started in the 90s, supported in part by one of the MRL's predecessor centers. It's an example that just happens to involve Vladimir Bulovic of electrical engineering. It also involved Amunji Bwindi of chemistry and Klaus Jensen of chemical engineering, highly interdisciplinary. A lot of it was carried out in Building 13. And it started with some amazing improvements in the ability to make what are called quantum dots made by Munjibwindi in chemistry. That then led, of course, to the study of these materials, especially photoluminescence and electroluminescence. And what's special about quantum dots and the synthesis route used here is you can make nanoscale particles, you can think of them as spheres, with very controlled sizes, large populations of them. And their size affects properties like photoluminescence. And so with the techniques that Munji developed, he could make particles that would photoluminesce at different wavelengths and give you different colors. Okay. So that then, so we have the synthesis, we have properties, and then that led to a new insight, and that is how to use these nanodots, or quantum dots, to make new devices where you can use a gallium nitride LED and then use quantum dots of a specific size to generate pure color, like red, or quantum dots of a variety of sizes to make a variety of colors from white to every other color you can imagine. That was an important idea. These have come to be called quantum LEDs. Shortly after this work in the 90s, Vladimir and Munji formed a company, QD Vision, to use these ideas not only to advance quantum LEDs, but other technologies as well. And then just a couple of years ago, Samsung bought this intellectual property, and it is the basis for how they make the QLED TVs that you hear so much about them. So this has all the elements: how you make the materials, what their properties are, and how you optimize their performance in a system, in this case, a new device, and ultimately how that can lead to commercialization. And this is a story that has happened many, many times. It's interdisciplinary, and it goes through all these cycles. Okay, well, it's not an isolated story. I'm going to end here with this chart, which is going to be hard to see from out there. You will see why I love this chart shortly. This is a fairly dated study at this point. It is the number of inventions by building. And one of the reasons we only use numbers is it would mess up a chart like this if we tried to say all the names. But anyhow, what you see is, you know, there's invention everywhere on campus. You see there's some spikes, but every building has invention. MIT.nano is going to raise all these bars because it gives us capabilities we've just never had before. I want to focus, though, on that big spike, and that turns out to be Building 13, okay? That's what, well, yeah, just coincidentally. And so I feel this is an illustration of why materials research is, illustrates how materials research is fundamental to technology in so many ways, including invention. Now, there's another bar on this chart, and that's Building 12. But this is an old chart. This is the old Building 12, and now the new Building 12 is MIT.nano. And whenever this study is done again, let's say in 5 years, we're going to see Building 13 left behind, but hopefully we'll both increase in our partnership. So with that, I'm going to turn the floor over to the speakers. We have 3 speakers. The first presentation is a keynote discussion of something I went over briefly, the entrepreneurial process. You may have noted there was 20 years in there, and there were ups and downs. And Kristen is going to talk about how we can shorten that time and how we can make sure that companies don't die between the beginning and the end. Kristen is Associate Provost at MIT. She's a professor of both material science and engineering and biological engineering. She has an incredible array of wonderful research, but we don't have time to go through that. She's going to talk about what she's learned in various capacities about the Valley of Death.
Good afternoon. So, as Carl mentioned to you, I'll be talking about the Valley of Death. May not sound like an an exciting or an exotic topic, but it's taken on really new excitement and responsibility at MIT, and MIT.nano is going to be a big part of that. And this is the valley of death of how you get these materials ideas that you heard about so much from Carl over a range of industries, sectors, disciplines, and sciences into the real world, into the market, and the manufacturing that that requires. So understanding this is how we are learning to make the future together, and materials are at the core of that. So let's start with an object that you may be looking at right now, but look at mine. So this is a phone. This happens to be my iPhone. You have your own smartphone. It differs in some ways. You might have a different manufacturer. You might have different apps on your phone. You probably don't have the picture of my husband and my godchildren as your wallpaper. But otherwise, the guts of this are very similar to the phone that you own. And I bought this phone, maybe you did too, here in Cambridge, not far from MIT's campus. But it wasn't designed here by MIT. In fact, it was designed here in Cupertino, California. And that is actually the largest single employer of MIT's mechanical engineering graduates. But this phone was not made in Cupertino, California. In fact, it was made across the world in Shenzhen, China. So when you think about how do you get from these great ideas of these materials that went into my phone and then got designed in California and produced in China and then sold back to me in Cambridge, right? This is what we think about. How do you get from innovation to production? And that question is important, not because all products will be made like your iPhone is made, but because most products will not be made that way for a very, very, very long time. The reason is because when we want to link innovation to production, you need in the middle an innovation ecosystem, a production ecosystem of people who know how to make new materials in new ways for new functions, for new devices, and really think about that holistically. And increasingly, as we heard today with the discussion of quantum computing, this production ecosystem will include not only people's hands, but robots' hands as well, and how to increase the augmentation and the capabilities that that provides. So the other advantage of learning how to make new materials in new ways at scale is we don't have to produce 1,000 cars that all look the same. In fact, we can produce every car differently. So to go from Henry Ford's production line to a fully customized 3D printed car, which is what you're seeing here. So let's think about that technology in particular. So 3D printing, invented decades ago, long before I ever came to MIT, actually before I came to Earth, right? So this was a way to make materials in a new way, and it was really a way to make toys, neat objects, sculptures. And that is still done with 3D printing, but it's amazing how in the decades that it's advanced, through innovation in materials, we don't just make toys, we are able to actually make a Shelby Cobra. So this is a photograph of just a few years ago, a car that was 3D printed in 12 weeks. 6 weeks for design, 6 weeks for printing, from 3D printers customized for this purpose. And this was a partnership between lots of researchers and the Department of Energy. Here you see our own Ernie Moniz, at the time, the Secretary of Energy, driving this Shelby Cobra to illustrate how you could go from printing small objects to printing large objects by understanding the materials processing that that required. And now, instead of just printing one really, really beautiful car, there are whole companies that will, on demand, 3D print your car for you. So it spawned an ecosystem. And that process for it to repeat, you have to think about how did I make that material in the first place? And how might it make it different for a different application? So here's another application. This looks like those fibers that you saw in the previous slide. These fibers were made by 3D printing, but they're very, very different. These are made in my lab. And what you're looking at here is the work of Anna Gagilska and Daniela Espinosa-Hoyos in my group, who have figured out how to 3D print fibers that are never going to go into a car, but are going to go into the next drug discovery systems. So these fibers are nanoscale to microscale in dimension, but the trick is that they have the exact geometry and mechanical properties of the nerves in your brain. And so what we're able to do is have these materials that we call artificial axons, long fibers with the mechanical, geometric, and chemical cues that the cells in your brain need to signal, and then interface them with living biological cells. These cells that they're interfacing with are the cells that are supposed to be creating the electrical insulation for the nerves in your brain. And through these technologies and these materials, we are able to now watch that happen. We can see cells in real time wrap around these artificial axons. And when that process works, you have proper conduction of neural signal. When that process doesn't work, that's a degenerative disease such as multiple sclerosis. So when we can watch that process, and we'll be able to do even better in MIT.nano, it's these nanoscale interactions between our artificial axons and the cells from the human brain that we're watching. And the new tools in MIT.nano will allow us to do that at high resolution for the very first time. So how do you get from lab to market these great ideas in order to commercialize? And so in this case of the example that we discussed with our artificial axons, how do we get from the idea, and in fact the science of how to do it, so that we can get such a device into a clinic, into a drug discovery operation, into commercial production? And to get from A to B, you can really think about this in terms of what it means of a graph. So the vertical axis here is money, it's investment or profit, and the horizontal axis is the production scale. And that's the challenge. How do you get from the idea to the production scale? And the big obstacle here is this valley of death in between, this low level of, I've had the idea, to get it to market, I have to overcome so many de-risking steps. How do I do that? And that's challenging in any market, but it's particularly challenging in CapEx intensive or tough tech technologies that use materials innovation. So the way that we have been working on this, MIT and many other partners in the country, is to form a new kind of public-private partnership. So this involves companies, it involves the government, and it involves academia, including MIT, so that there would be impact not just on MIT and Cambridge and a company like Apple in California, but impact throughout the country, so lots of people's great ideas can make it to market. And so one manifestation of this that MIT has been involved in for a number of years is something that's now called Manufacturing USA. I'm showing you here 14 Manufacturing USA institutes. Each of them is focused on a separate topic, a separate type of manufacturing. But almost all of them, at their core, are driven by new ways to make, measure, model materials. So I'll show you as an example of that. Here, a subset of the Manufacturing USA institutes. MIT helped create this network. MIT participates actively in 10 of the 14, but I'll show you just this subset. So if you think about using light in terms of a new way of passing information like electronics, that's integrated photonics. You heard some of that today. You heard Eric Evans mention that Lincoln Labs is playing a major role in integrating those technologies, and MIT is as well. So one of the manufacturing institutes is called AIM Photonics, focused on how to make those devices reality and commercialize them, much like the semiconductor industry did decades ago, as we heard earlier from Ray Stata. But if we can connect how to make integrated photonics with how to make functional fibers in another manufacturing institute headquartered in Cambridge, and then work with additive manufacturing, generally also called 3D printing, in another part of the country to put those tools together, we can produce products that are also known as flexible hybrid electronics. And you saw this in the previous examples of using roll-to-roll printing from Karen Gleason's lab. So here you're putting different parts of materials manufacturing capabilities together at the same time as the workforce. And then you want to automate and augment that workforce with the use of robotics for manufacturing, another topic. And finally, you don't want to just make those great new technologies and throw them away, especially when they include so many precious materials. So you want to think about how you would design the materials and the devices with recycling and recovery in mind from the outset. And so this is an example of how these Manufacturing USA institutes can work together. They're not buildings, they're networks of people and ideas, very much like MIT.nano is not a building. It's a network of communities, people, and ideas to make this happen. So as an example of how this is working right now and how MIT.nano will further enhance that, we'll take a closer look at AIM Photonics. So as I mentioned, this is a Manufacturing USA institute focused on making integrated photonics a reality, using light on top of silicon devices to pass information faster and better and enable some of the amazing technologies that Eric showed us just a moment ago. This institute was started and founded by folks around the country, including Mike Watts and Kim Kimmerling from MIT. So faculty, along with companies and the government, had this idea to do this. And it's grown into being able to make new kinds of devices at Lincoln Labs in New York State, and with MIT.nano here at MIT as well. So this will be a new way of making new kinds of devices where we've only so far just scratched the surface. Then people will be learning how to actually use those devices and train on that manufacturing equipment, and think about entirely new kinds of careers that just didn't exist even 5 years ago. So here's a photo of Sean Reese, who actually spent this past summer at Lincoln Labs learning about integrated photonics manufacturing through a program developed here at MIT called AIM Academy. And now, this week, he's starting his degree program at UMass Lowell. So that's the kind of integration and impact we're having. So as excited as we all get about making new things, making new devices, making new materials, making new companies, that is only part of the production cycle. And so MIT.nano and the folks who work within it will also be thinking a lot about not just the production, the packaging, the sales, the distribution, but also where did these materials come from? Where do they go when I'm done with that product? How can I do better in terms of closing the loop, this particular loop? Because in order to have sustainable production, we have to have sustainable materials manufacturing. And you know this is true, but you don't always let it be a part of your everyday thought process. The lithium-ion batteries in my phone come from materials that are originating from countries very different from the US, although they also exist in the US. But this photograph I'm showing you is from the salt flats of Bolivia, one of the poorest countries in the world. So where do those materials come from? How can I make responsible use of them? How could I perhaps even replace them? Some of the devices in my phone rely on the performance of materials that right now we get from the Democratic Republic of Congo, a highly destabilized country, in part because of the demand that we all put on the materials we use in advanced electronic devices. So how do we think about that as materials engineers, as consumers, as people in society? And this happens even within a country. I'm showing you here a photograph of a person whose everyday job is to bring back rare earth metals from water-flooded mines in China, but I could show you pictures from many other countries. But this is the same country where I told you Shenzhen has a plant making iPhones, right? So it affects the labor, it affects the resources of the earth, it affects how people live in countries and communicate between countries. So when you take apart your phone, and I don't recommend that you do this, but we have every freshman in my class do this, and they really enjoy it. So when you take apart your phone, you'll see some very interesting things. One of the things you'll see is that many parts of your phone have handwriting on them, because there are real people assembling these, putting these materials together. And thinking about how we do that and how it affects the earth is an important part of being somebody who works on materials innovation. So here's just one chart from a very interesting study that I completed a couple of years ago with Professor Elsa Olivetti, also in materials at MIT, to show exactly how much materials, and therefore money, we left on the table by not fully disassembling and taking the materials out of these phones. We did a study on just the country of Portugal and all their phones. But the amount of gold left on the table from phones in the US is literally tons. So in order to close that loop, circular economies need to have manufacturing sustainability, including sustainability about the material selection and processing and reprocessing as part of what we do. And MIT.nano will enable us to have new ways to do that. So it all starts with mind and hand, but also materials. You've seen that that has been so central to the talks today. And it's not an accident that the Latin word for materials has the root mother, right? Because materials are the mother of all invention. I believe that. That's why I work in this field. And so as we think about how to make materials, model materials, measure materials, and also manufacture them, that is part of what we will do to help make a better world. And next, you'll hear just a couple of vignettes into the excitement around modeling materials from Marcus Buehler and measuring materials from Francis Ross. These are the kinds of examples that we're going to be able to see more and more of in the next generation of materials engineers who learn how to live and work at MIT.nano. So thank you.
Thank you, Vladimir, for the invitation, and congratulations on a really great day and a great new building and community. So my presentation, which I think will be coming up in a second here, we'll be focusing on how to make nano big with what we call materiomics. And I'll talk about the different scales we have in materials. So let's begin. So if you look at a material at a very large scale, you might think of it as a building, like an Eiffel Tower, for instance. And if you take a virtual microscope and you go smaller and smaller in this building, you can see that actually it consists of steel trusses. The steel trusses themselves consist of smaller scale trusses and elements. And individual steel trusses become visible at some point. And if you look even closer, you begin to see the nanoscale or mesoscale, even smaller scales. You begin to see microscopic fractures. You begin to see individual molecules. You begin to see individual molecules maybe sliding. And ultimately, you see the chemical makeup of materials. And so this is really how we like to look at the world. And really, what MIT.nano allows us to do is to engineer all of these scales. And that's something that we have been pursuing in our laboratory for many years. And MIT.nano is really a dream come true for us because we'll be able to measure and make and produce materials that perform very highly at all these different scales. So if you think about these different scales, I'm going to talk a little bit about how these things look like in nature. And in fact, natural materials or biological materials, like what you see here is an in situ imaging scan of a 3D spider web, actually show naturally a buildup of multiple scales. So nature is a nano engineer, has been a nano engineer for many, many billions of years. So what you see here is you go inside a spider web, and you can see more and more details as you go inside the spider web. And if you go even into greater details, you can see that this spider web is made from spider silk. You can look closer, you can see that individual fibers actually are made from components of bundles of fibers, which in turn are made out of bundles of even smaller fibrils, which in turn are made out of nanocomposites of proteins. And these proteins form two main structures, almost like a brick and mortar structure that we use in building a wall, for instance. And these brick and mortar structures are then itself composed out of the chemical elements or amino acids or proteins, right? And so you can see that this material has an amazing structure. And you see the spider web structure by itself is beautiful, but if you look even closer, you can see a really hierarchy of structures in there. Now, what's interesting about spider silk is if we compare the spider silk to engineered materials like steel, steel has a strength of gigapascal or more. Spider silk actually has the same strength, and strength is measured as force per unit cross-sectional area, so it's a fair comparison. Spider silk is very thin, so if you take a spider silk thread, it appears very weak, but it's also very, very tiny, only a few micrometers in diameter. But if you compare the strength of steel and spider silk has about the same strength. Silk, though, is much tougher, and it takes very, very significant energy to break because you can strain it by 60%, meaning you can almost stretch it by its initial length until you have breaking. Now, what's interesting is that steel is made from strong bonds. Spider silk is made from weak bonds, hydrogen bonds, which are basically the bonds you have between water molecules. And the key to make weak bonds, like in liquid water, become as strong as steel at the macro scale are these hierarchical structures that we see. In fact, the conventional engineering doesn't take advantage of this. In many cases, the way we make materials like concrete or cement, for instance, or steel, many other materials, we take something from nature, we heat it, we break it up, we grind it, and in the case of concrete, actually producing a lot of carbon dioxide in its way, and we create cement powder, which we then put with water, and it sets, it becomes concrete. Similar things happen in the production of pretty much any engineering system today. So what we're trying to do is to turn this around and follow nature's approach in building things bottom up. We use few raw materials. So the spider web actually consists of a very simple chemical component, protein. We create enhanced flexibility, many different functions through structures. So if you imagine spider silk, spider webs, but also our human cells, hair, our skin is made from the same basic chemical building blocks. So living systems, very complex systems, are made from the same chemistry. So this is a really fantastic, amazing property, of course. As an engineer, we can create many different properties from the same raw material. And also, what's really important, of course, in the bottom-up approach is that we can integrate the making of material, the production, with the actual application and use of the material. And this is what we call the bio-inspired approach. This is very exciting. And in fact, sort of a little schematic of how this works in nature, a lot of times we have the DNA, which encodes the information about the structure from the nanoscale. Typically, cells and organisms produce fragments of proteins or other biochemicals, which then are put together in processing. So the processing is really important, how these multi-scale structures are built. And eventually, the material creates a spider web, a filament or spider web, or any kind of structure we might see in nature. And this here actually is a photo of a real spider silk spinning die. So this is how nature produces these steel strength cables. This is a real photo, but with added color, you can see this. So it really goes from making a liquid into a solid. Now, how do we study this? So Kristen mentioned already, we're doing a lot of modeling. So modeling is really key. So if you imagine the future nano engineer needs to be able to model and simulate many different scales in the material. We actually begin by modeling at the quantum mechanical scale because, of course, at the nano scale, we have amazing new effects that are governed by quantum mechanics. But we need to bridge these scales from nano to macro. And ultimately, we want to make these materials. And so what's really fascinating with the advance of computing, we can now not only simulate and model and design materials, we can actually also make them straight out of the computer model. So the movie you see on the right-hand side is a little bit of an animation of 3D printing, which can be directly coupled to these models. So let's talk a little bit about why is this relevant. So one example I can show you is fracture. So all of you have dropped a piece of glass, and this is sort of how this looks like. So it looks pretty fragmenting. And the other example of fracture is more dramatic, maybe an airplane disaster. This is an airplane disaster, very famous in the 1980s, where a very tiny crack began this failure process, which led to the entire airplane to break. And the kinds of things we can begin with to do with MIT.nano, we can actually visualize and image these nanoscale cracks real-time in situ and study how they propagate. In fact, when the airplane breaks or the glass breaks, this fracturing begins by breaking atoms by atoms. And this is what you see in these. On the left-hand side is the experiment, right-hand side the simulation. And we're now able to actually match quantitatively in situ experiment simulation and watch fractures propagate. So this is an incredible opportunity designing stronger, lighter, cheaper materials, more sustainable materials. Other things we can do, we can actually apply this sort of engineering to create entirely new materials. So this is a couple of examples how we used silk, proteins as a basis to create many different things. We can create hierarchical helical silk for flexible electronics or nano springs here on the top. We can create filtration devices, and we can create extremely strong material, even stronger than natural silk. And the way we do this is by engineering all these different scales. We take the nanoscale building blocks and we engineer them at different levels and design them and make materials with entirely new properties. And this is another movie that shows if you take this nano spring made out of silk into a very cold temperature, this is liquid nitrogen, so very cold, minus 300 degrees. And any material that you would take in this room would probably break in these very cold temperatures. Of course, the silk material has been designed to withstand these very, very cold temperatures. This is a kind of thing you can achieve, very new properties you can achieve at the macro scale by engineering these materials at the nano level. Sort of a game changer for us in this field is actually using machine learning for material design. So instead of solving Schrödinger's equation and Newton's laws, we can now go ahead and actually let computers rediscover these fundamental foundational physics and chemical equations. And what we have done in this area, sort of going away from a situation where we have boundary conditions and finite element models or molecular dynamics models, but feeding instead data about experiments, data from computational simulations into a machine learning system, which then can learn by itself relationships between variables and carry out optimization and design. And so what we can do with this, we can design entirely new materials very fast. So for instance, what you see in this video here is we've designed materials that are highly impact resistant. And the solution to these problems, by optimizing a nanostructure and microstructure, would not be feasible with conventional models. But machine learning is a gateway for us to do these kind of optimizations very rapidly. And then we can make these materials using advanced manufacturing techniques, as we've heard earlier, like 3D printing in this case. And we can come up with entirely new designs, which we couldn't have been able to make just a couple of years ago, but now we can actually produce them. And shifting gears, you think about the spider web, not only can you see the spider web and actually watch it, you can also hear it. So in this work here that we're doing with the MIT CAST group, Center for Arts, Science, and Technology, we have found a way of using the spider web and the data of different levels and sonifying that, so making it audible. So what you hear in the back is the actual audio of the spider web. We can use the spider web interactively and create a musical instrument. What you heard here in this audio actually was we've used the spider web as an instrument, created a new musical structure, new sound, new audio, which in turn can be used to design new materials. We can take the data back that the composer has created here and actually use this data to create a new silk sequence for new materials. So these are some really creative, out-of-the-box ideas. We have to interact with multiple scales in this material, to interact with scales we cannot easily see, but maybe we can better hear them, and we can construct them in that way. It opens the door for many multidisciplinary cooperations that we have been able to do here at MIT, and it's an exciting place to bridge these disciplinary boundaries. So thank you very much.
Well, thanks everyone for your enthusiasm staying through the afternoon. It's a pleasure to have a chance to share my enthusiasm about the new MIT.nano capabilities and how they're going to impact our interests in basic science and applied science as well. So I'm Frances Ross. I joined very recently in the Department of Materials Science and Engineering, and I'd like to talk about characterization and materials design and how we're going to take this forward using the new capabilities that are allowed by the nano building. So as materials scientists, our grand challenge is really, as Carl said earlier, to design and build materials with particular properties, whether those properties are electronic or mechanical, or whether they involve production with low cost, whatever it may be. We often use nanoscience as a tool because when we shrink the dimensions of materials, we often unlock new properties by doing so. And so building materials where you have precise control of all the atomic positions on the nanoscale is truly a grand challenge in materials science. Now, it's often done by using techniques such as scanning probe microscopy to place each atom in position in the nanostructure. And what you can see in this image is an example where this is done. Each magnetic atom was placed in position one at a time to create a very small magnetic bit, which is possibly useful for high-density memory elements and also for fundamental studies of magnetism at the atomic scale. However, it's obvious that this kind of approach will not work if we need to make a large number of objects simultaneously, because it will take too long. So for larger numbers of objects, for parallel construction of nanoscale objects, we often turn to self-assembly. And so here's an example from the other day when it was raining on the nano building. These raindrops all assembled into hemispheres. We didn't tell them to do that, but the surface tension of the water and the properties of the glass-water interface forced this material to form in the shape of hemispherical droplets. So we can generally use self-assembly to make large numbers of simple objects, all in parallel, often very cheaply and simply. So here's our question. Can we use simple self-assembly processes to build more complex structures. And as I said with the water droplets, self-assembly is generally the atoms following a pathway of, for example, controlled by simple physical phenomena, the surface energy, the pathway with the lowest barrier to get to the final structure. So what we find is that if we can understand the physical processes that underlie self-assembly, we have a much better chance of controlling self-assembly so that we can use it to make more complicated structures. So electron microscopy provides a way to at least go some way towards this goal. We use transmission electron microscopy because it provides high spatial and temporal resolution, and we can make movies of particles assembling and reacting as the process takes place to give the atomic level details that transform our understanding of the process. So here's a photograph of a microscope. You can see it's a fairly complicated looking thing. There's the microscope. There's a lot of additional chambers on the side. And this kind of highly customized equipment allows you to place a simple structure within the microscope, such as a flat surface, and then to add other materials, change the temperature, change the gas pressure, and then make a movie of a reaction taking place within the microscope. And then by analyzing the movie frames, we can pick apart the physics that underlies the process. So I'll show you a few examples. I have to say the movies are not as spectacular as what we saw earlier, zooming through the pathway in Puerto Rico, wherever it was. But because the electrons are all the same color, these are black and white movies. But the scale of this is rather different. So I'm firstly going to show you a movie of what happens when we start with flat silicon, and then we add germanium atoms one at a time, and we watch how they spontaneously self-assemble into small strained islands called quantum dots. So let's see if this works. As we start the deposition process, you can see lots of small islands forming. And look at, as it goes on, look at the smaller ones. Do you see how the bigger ones are growing and the smaller ones are shrinking away? So this is like economics. The rich ones get richer, the smaller ones eventually lose everything they started with. And the really surprising thing about this movie was the strength of that dissolution process. Even though we're adding more material, these small islands are still losing material more quickly by surface diffusion, where it joins the larger island. So this process, exchange of the germanium atoms between the islands, dominates the growth of the final array of germanium quantum dots. And by developing models that make use of the understanding of physics that you get from the movies, it's possible to devise means for making arrays of identically sized quantum dots for applications like quantum cellular automata, or, for example, to control the light emission from the structures. So the next example is a little bit more complicated. This is a catalytic process at work. Now we can supply the growth material from a gas phase to the surface of a catalytic droplet, where the material will start to dissolve into the catalytic droplet and eventually get deposited at this interface. So look at the movie as it plays, and what you see is a kind of a pulsing motion, right? So what we're watching is the growth of a nanowire. This is silicon. You can see it's getting longer, and from these movies we can measure the details of the growth process. For example, one very obvious observation here is that the growth is not continuous. Even though we add the material in a continuous fashion, the growth tends to be jerky. There's a pause, and then a new layer of atoms adds, then a little pause, and then another layer of atoms adds. So in this movie, each one of those little stripes, each layer of atoms, is 3 angstroms higher than the previous ones, 1/3 of a nanometer. So very fine scale details of the growth process that help us to use this kind of self-assembly process with catalysts to generate much more complex structures that make use of the properties of the self-assembly process. So let's, as I mentioned before, one of the things that's interesting about these types of structures is that we go from imaging, we can not just image structures as they form, but control their properties and measure their properties. So it's possible, for example, to do a growth experiment from one location to another, forming a bridge from a nanowire, and then still in the microscope, use that for measuring the electrical properties of the structure. So for a single nanoscale structure, we can measure its electrical properties and correlate with the positions of the atoms in the structure. Now, everything I showed you so far was done by adding gases into the microscope. So we're flowing in gases, we're making a movie of a reaction as it takes place. You can also look at processes that take place in liquids if you're careful to separate the liquid from the vacuum that's normally within the microscope. So this type of thing, of course, first done by hand by graduate students who spent hours working on this. So they produce a thing that doesn't look that pretty, but is nevertheless able to generate movies such as this one, which shows the deposition of copper using electrochemical processing in a liquid, in an aqueous solution. This is the process used to make copper interconnects within integrated circuits. And we're measuring, as you see here, the structure as it grows, plus the electrical characteristic of the process. And so materials reactions in liquids, especially water, are very important in a whole range of areas that impact real life. This is a series of stills showing the process of recharging a battery. The instabilities that sometimes form if you charge too quickly will generate battery failures if you don't do it correctly. We can look at corrosion, an absolutely important problem that consumes several percent of the GDP. And here's a single aluminium grain where we see pits that form within the structure of the grain. And it's very hard to image this type of process without in situ capabilities. And finally, one of my favorite movies, the formation of nanoscale bubbles within a liquid cell, and these bubbles are only a few tens of nanometers across. We can look at how they nucleate, how they coalesce, how they move within a confined volume, which is important for catalysis, cavitation, or corrosion. So let me bring this all to a kind of a head by saying that the developments in characterization techniques are essential for pushing nanoscience and nanotechnology forward. We need to be able to see what we're doing and to see how the material is being made. So what we are excited about with the nano building is the opportunity to improve these types of characterization tools using the very quiet environmental rooms that have been built in the basement. And so if I'm going to show you now an older movie, which is the growth of and reaction of gold triangular islands on a graphene surface. You can see they're actually moving around. See, they're sort of jumping here and there, and one of them will rotate. This is an experiment designed to image the interaction between nanoscale materials and the new two-dimensional materials which have different chemical bonding opportunities on the surface. To do these types of experiments, to acquire the high-resolution information that's necessary to truly understand what's going on, we need several ingredients: a very stable room, a microscope that's capable of imaging with low-voltage electrons that won't damage the material, and high resolution in both space and time. And with the new nano building basement area, we can start to evolve our development of characterization tools so that we can really start to probe these types of materials reactions and really go after our objective, which is to measure the details of self-assembly processes in general, to identify the pathways by which the atoms get to the nanostructure, develop new models for growth, look at unexpected processes, and use that understanding to really develop new types of nanoscale material. So thanks for your attention.
All right. You know, we need to give you a break, so we're going to spend about 10 minutes milling around, and then we'll come back with the last session of the day, the design session. Thank you.